Good morning, everybody. This is lecture 9 on our statistical computing and machine learning course. I am Professor Nicolas Zabaras, and today we will discuss about a few more aspects of the multivariate Gaussian, and in particular on how to be able to manipulate a multivariate Gaussian to get things such as conditionals, marginals. All of this algebra is going to be very essential for many aspects of our course, so it's a good idea to visit carefully some of these developments so you know where to find formulas that you will need in subsequent lectures. So let me review briefly what we will cover today. So we will see a few basic things about some geometric aspects of the multivariate Gaussian, all of them based on an Eigen expansion of the covariance of the multivariate Gaussian. We will formally see again the Mahalanobis distance. We will see some plots of equal probability contours for at least the two-dimensional multivariate Gaussian. We will show how, or at least we will highlight how you compute the moments, things such as the mean and the variance for the multivariate Gaussian, and then also the limited cases of the multivariate Gaussian, and just say a few words also on how later on the multivariate Gaussian is going to serve us in a big way in other aspects of machine learning. All right, so we will then expand to discuss some linear algebra type of calculations. We will introduce conditionals and marginals of the coming from the multivariate Gaussian. We will introduce what is called this Sherman, Morrison, Woodbury formula. That's very essential for many calculations. We will see, for example, it's a very essential type of calculation when you work with Gaussian processes. And we will give a few examples. And finally, I'm going to finish with some not necessarily very trivial examples where these ideas of the manipulating the multivariate Gaussian are being used. So I'm going to show you how we can do interpolation with noise-free data. So, if I give you a few data and you need to interpolate in between them in space or time, we will see how we can do this with the assumption that the data follow a Gaussian distribution. We will bring up the concept of a smoothness prior, and also we will talk a little bit about data imputation. And in closing, I only want to spend a few minutes to give you an alternative parametrization of the Gaussian that goes with the name of information form of the Gaussian. So up to now we have used what is called the moment parametrization, writing the Gaussian, for example, in terms of the mean and the variance. So we will see the new parameters that are being used for the so-called information form of the Gaussian. All right, so the goals for today's lecture are to understand the various transformations of the Gaussian variables and understand how to plot in 2 dimensions equal probability contours. We will calculate the moments of the multivariate Gaussian. We will give you formulas that you need to become very familiar on the conditional and marginal Gaussian distributions. And then we will use these formulas to perform interpolation in a noise-free setting, and I will also discuss a little bit the noise case as well. And then we will also use this to do what's called data imputation in general. And finally, I want everybody to at least familiarize themselves with this canonical or information form of the Gaussian, because later on, especially when we talk about the exponential family of distributions, this may come to be a useful representation for the multivariate Gaussian. Okay, the references remain at large the textbooks from Chris Bishop and Kevin Murphy. Kevin Murphy's chapter 4 is completely devoted to calculations with the multivariate Gaussian, and various aspects that we will use today are also embedded within chapter 2, but obviously the slides here provide a little bit more details and some derivations that you will not see explicitly in these books. Okay, so let me remind you the form of the multivariate Gaussian. So we start at least with the basics. Here is the equation, sigma, the covariance matrix, the determinant of sigma. This is a multivariate Gaussian in d dimensions. And I remind you that sigma is a symmetric positive definite covariance matrix. Okay? All right, so let me remind you the Mahalanobis distance. So this is, you can think of this as a generalization of the Euclidean distance. As a matter of fact, if the covariance matrix is the identity, you do get the Euclidean distance. So if you remember, if I can go back to the previous equation, the Mahalanobis distance comes in the exponential of the multivariate Gaussian. So if you really want to have contours of constant probability for the multivariate Gaussian, those are effectively contours where this quadratic forms becomes constant. So effectively, where that delta square that you see there is constant, that will lead to equal probability surfaces for the multivariate Gaussian. Now, I am not going to do the algebra, but for those who have some of you have seen this before, you know that if sigma here was not symmetric, all right, and you split this sigma inverse to a symmetric and anti-symmetric part, you can show that the anti-symmetric part, when you do this operation that you see on the right hand side here, you get a 0. So effectively the Mahalanobis distance is independent from the fact or not that sigma is a symmetric matrix. But with that said, in our calculations, obviously sigma is a symmetric positive definite covariance matrix. Okay. So if sigma is a symmetric positive definite matrix, what we can say from linear algebra is at least that sigma has a complete set of orthonormal eigenvectors, and we can write down an eigen expansion of sigma that looks, let me start with the eigenvalue problem for sigma. So the eigenvalue problem will look like this. Lambda I are the eigenvalues, and ui are the eigenvectors that here, as you see, they have been normalized. So ui is orthogonal to uj, but also I make the magnitude of each of these eigenvectors to be equal to 1. So if this is the eigenvector equation for the covariance matrix, you can actually write down the equation, the expansion for the covariance matrix in the way that you see on the top. Okay, so don't forget that ui transpose is a matrix, right? So the covariance matrix is written like that. That's an eigen decomposition of sigma, and the inverse of this is 1 over lambda I with the same basis here, ui transpose. All right, so what I'm going to try to start now doing is I am going to define sort of some new coordinates to represent the Gaussian, so and especially this equal probability contours. So I'm going to try to move away from x to some new coordinates so that this equal probability contours become ellipsoids. So I'm going to show you how this sort of algebra is going to look, with rather simple calculations, where the only thing that I'm going to be using is the orthogonality of these eigenvectors ui. All right, so let me introduce a new coordinate system. So you remember we started with the vector x with coordinates x1 and x2. Now I am going to define a new coordinate system y1 and y2. And how do I define them? So yi is ui transpose x minus mu. So effectively, you can think of taking your vector x minus mu, so it's a shifted location, shifted by the mean, and I'm projecting it to the vector ui. So really, these coordinates yi are the coordinates of x minus mu in the directions of the eigenvectors. And I believe the next slide will actually geometrically show you this type of calculation. So I can write all of these components in a vector form, and in a vector form they will look like that. So y is equal to u times x minus mu, where in my notation this orthogonal matrix U is going to have rows that are given by the eigenvectors ui. So remember, in the way that I introduce U, each row in U is an eigenvector ui. Okay? All right. So U is an orthogonal matrix. As we mentioned, right, for the symmetric covariance matrix, the eigenvectors are orthogonal. So U transpose and U transpose U equal to the identity matrix. And this type of calculation is going to be handy as we move forward. All right, so this is the geometric picture that I mentioned before. We shift x by mu, and then we project x minus mu to the axis in the directions of u1 and u2, and I'm plotting this, of course, here in 2 dimensions. And then these equal probability contours take this simple equation, and for those familiar with geometry, they can recognize directly this as an ellipse, where these semi-axis of the ellipse are the square root of lambda 1, and this is the square root of lambda 2. Okay, so our new axis to represent these equal probability contours are oriented in the directions of the eigenvectors. So in principle, the only thing we have done is take the coordinates x1 and x2 and rotate them with this orthogonal matrix U to the direction of the eigenvectors u1 and u2. Now you can actually do lots of fancy calculations, even not just in 2 dimensions, but in high dimensions. So if somebody, for example, asks you in high dimensions, what is the volume of, I may say, hyperellipsoid in d dimensions, you can actually do the calculation relatively easy. So in the y coordinates, this will be the volume of the hyperellipsoid, and if you do a transformation from y to some new coordinates z, where zi equal yi divided by square root of lambda, so you're going to have to change the integration. So here, with change of variables, you're going to get this product of the square roots of the eigenvalues, and then you're going to get this integral of these products of these z's. All right, and you can see actually when you define zi to be yi over square root of lambda I, effectively what you get is this equation becomes the equation for a sphere. So this becomes the volume of a sphere, and just, you know, without any proof, and maybe use your imagination here, the volume of a sphere that has radius delta is given by the volume of a sphere of unit radius times the radius delta to a power d, where d is the dimensionality of my multivariate Gaussian. Okay, and this product of the square roots of the eigenvalues is nothing else but the square root of the determinant of the covariance metric sigma. Remember that if you represent sigma in the eigenbasis in the direction of the eigenvectors, sigma is diagonalized So you have lambda 1, lambda 2, lambda d in the diagonal. So when you take sigma 1/2, you have square root of lambda 1, square root of lambda 2, etc. And the square root of this determinant is nothing else but this product. So again, simple calculation allows you to actually compute either the area or the volume of this hyperellipsoid. All right, so let me continue with some calculations with the multivariate Gaussian. I'm going to try to highlight some of the key ingredients of the derivations and the final results. So if the algebra doesn't make a lot of sense, you know, in first passing, you can just omit most of the calculations and only concentrate on the final results. All right, so remember that I had written down the new coordinates y, transforming x to y, and obviously the question that somebody may ask is, can I write down the inverse transformation? Can I also figure out how x is transformed to y? And the answer is yes, we can actually do this, okay? And the way you can do this is, remember that the U matrix is every row is this eigenvectors uj. So really I can write down this inner product as uji times xi minus mu I with summation in I. Okay? So effectively what I am doing here is I am using the definition of the U matrix. Okay? So, so this is what yj is. And now what I'm going to do is to be able to extract x in terms of y, I am going to use the orthogonality of u, so that u transpose u is equal to the identity. So what I'm going to do is I multiply with u transpose, and I sum in j here. And again, I multiply with u transpose, and I sum in j. And this product here, ukj, uji, sum in j, basically gives you a delta function ki. So effectively from this double summation I get xk minus mu k, and then I can discover that xk minus mu k is the kj element of u transpose times yj. So pay attention here, maybe my notation is confusing. This is the kj element of the matrix U transpose, where originally again I define U to be the matrix that has rows, the eigenvectors uj. Now, if you take the Jacobian of the transformation, del x del y, and of course you can guess where I may need this Jacobian, because at the end of the day I would like to produce the probability p of y starting from the p of x, which we know what it is, right? It's a multivariate Gaussian. So this Jacobian of the transformation can be written from this equation explicitly by taking derivatives as so the ij element of the Jacobian is the aj element of U transpose, okay? So the Jacobian matrix is U transpose, and immediately you can see that the determinant of the Jacobian from the calculation that you see on the bottom, and using the orthogonality of U and also this nice property of the determinants, you can immediately see that the Jacobian of the transformation is equal to 1. So effectively, in the calculations that are to follow, effectively to get the probability density in y, I only have to take the probability density p of x and substitute x in terms of y, and that will actually give me the correct p of y, because the Jacobian of the transformation, it turns out to be equal to 1. Okay. Let's try to do this type of calculation. So I remind you, we saw this before, that the determinant of sigma square root is this product of the square root of the eigenvalues. So, and I just mentioned to you the transformation from p of x to p of y. So the Jacobian determinant is equal to 1. So P of y, the only thing I have to do is replace my x's with my y's. You had seen this equation before, all right? So I can actually remove the summation and replace it with a product, and then by a miracle of algebra, you can see that the probability density of y is the product of d probability densities of univariate Gaussians, each of them with with variance lambda j, okay, and mean value equal to 0, okay. And because obviously when you look at these univariate Gaussians, they're already normalized, I don't really have to convince you that P of y obviously is normalized itself. So somehow by moving to y coordinates, we have been able to uncouple, if you like, this multivariate Gaussian and factorize it in products in a product of d univariate independent Gaussian distributions. Okay, so a very simple transformation leads us to a product of d independent univariate Gaussian PDFs. Okay. All right. So let me continue, and I'm going to discuss a little bit on how we compute the mean and the variance of the multivariate Gaussian using this type of calculations that we have seen. And I think I may have discussed in passing obviously all of these formulas, right? So some of these calculations may be sort of a repeat, but this is an appropriate place to have all the results together for the multivariate Gaussian, so I am going to redo it. So my apologies to those who will hear about this twice. So if you want to find the expectation of x, I am using just the definition of what the expectation is, and I'm doing a simple substitution. I am using x to be z plus mu, okay? So this is my simple substitution here. So x minus mu is going to become a z. The integration dx and dz become the same thing, okay? And I don't have to worry about the change of probabilities or anything because this is here p of x dx, right? So this becomes p of z dz, so I'm fine. And this integral is actually immediately available to us because the first term z times this quadratic term, when it's integrated, it gives you a 0 value because this is positive, and this is integrated from minus infinity to infinity, so it's an odd term. So when you integrate it, you're going to get minus and plus terms that cancel out. So this first product will give you a 0, and the other product is going to give you mu because mu comes outside the integration, and the remaining parts are nothing else but the normalization of a multivariate Gaussian, which gives you 1. So the answer to this is that the expectation of x is equal to mu. The computation of the variance is a little bit more involved, so I'm going to do the same type of substitution, and I am going to get rid of terms that have, for example, the term z mu transpose or the term mu z transpose, because those terms that only involve z will actually drop down to 0 as discussed before. So the only things I am left are effectively this term mu transpose and z transpose, and effectively what we need to discuss is on how to compute those two terms together. There is a little bit of algebra, so what I'm going to do is I'm only going to highlight the type of calculations and substitutions in these integrals that you will need to do, and you guys can read the details the details on your own. So the first term is actually trivial because mu transpose is constant, and the rest is the normalization of the Gaussian. So effectively, I do get the answer comes to be mu transpose. Okay, so nothing fancy with that. So what we need to do is we need to spend some time to see what's going on with this second term, which is the second moment of z effectively. So I am transforming again, as we have done before, the quadratic, the Mahalanobis distance in terms of the y's. All right, that's what I had before. There's nothing yet fancy. And then let's see what we're going to do is we're going to simplify this equation, and I remind you this formula we got for the relation of x with the y's. Okay, we got this relation of x with the y's, and I'm sorry, the x with the y's, and you remember I call x minus mu, we substitute z to be x minus mu, so this equation becomes zk times the kj element of u transpose times yj. I am going to use the definition of the transpose to substitute this awkward kj element of u transpose as ujk. Nothing fancy. And actually what I can do is I can write this equation here in a vector form as z, the vector z being summation of j from 1 to d of the eigenvectors uj times yj. And you may want to actually verify that this equation that I have here, zk equal to this summation in a vector form, is written like that. And the only thing I am going to say is that the k component of the eigenvector uj, it's actually the jk component of the orthogonal matrix U. So let me repeat, the k component of the vector uj turns out to be the jk component of U, okay? And that's how this equation that you see here leads to this vector equation that you see over here. All right, so what we're going to do is we're going to substitute this z in here, and the equation is going to become a little bit complicated because we have two z's. So we're going to get two summations, okay, yi, yj, summing from all possible sizes and j's, okay. You know, so I plug in things, all right, and you know, so effectively what I get is I get this integrals with double summation in I and j, and by the way, dz we can write it dy, because you remember, right, I mentioned I derived this before, the Jacobian of the transformation is equal to 1. So what we have is we have to compute these nice integrals. Now let me use your imagination here. Will you agree that if I is not equal to j, all right, each of these yi's, which is an odd function, we have to be integrated separately in the yi direction, and because this is an odd function with an even function, the integral from minus infinity to infinity will give you 0, both for the yi and the yj terms. So the only thing that will give you a non-zero contribution here is if I and j are the same, and that's what it's written here, okay? This is what is written here. And actually, if you pay close attention, all right, each of these terms in the denominator and each of these exponential terms is a univariate Gaussian. So the integral with of yi square, it's really the second moment of a univariate Gaussian. Okay, so I can split right this to univariate Gaussians. Okay, and the variance that you get is nothing else but the second moment minus the mean square, and the mean of y is equal to 0. So effectively what you get is you get summation of lambda I times ui transpose, which is the covariance matrix sigma. Okay, so all right, so we have done this calculation for this second moment, okay, and that gives us the for the second term, it gives us this covariance matrix. And again, the key ingredient of the derivation is that these summations only give you non-zero values when I and j are equal to the same value. So the double summation becomes only a summation in I, and then taking the yi term from this summation times this normalization factor times the yi square, I get the second moment of a univariate Gaussian, and then at the end of the day I have the covariance matrix sigma. So if you put all of this together, remember in our calculation, so this is what the second term gave us, but you remember in our calculations we had we had two terms, one that gave us mu transpose, and one term that gives us sigma. So this is basically what we derive if we put the calculations that I had earlier all together. So there were two terms left in the second moment. The first one was mu transpose, and the second was the covariance matrix sigma. So you can immediately see this minus that by definition is the covariance of x. So the covariance of x is actually equal to sigma. Okay, so that's a formal proof with this sort of change of coordinates from x to y and z, that the covariance of x is equal to this symmetric matrix sigma. Now the fact that sigma is a symmetric matrix means that in d dimensions, to actually describe it, you need d times d plus 1 over 2 independent parameters. So effectively you need all the elements below the diagonal plus the elements on the diagonal. And if you also account for the fact that you need d values for the mean of x, in total, for a multivariate Gaussian in d dimensions, you need d times d plus 3 over 2 parameters. And obviously you notice that this grows with quadratically with d, so that's not very good news. And that's why in practice we always try to work with some restricted forms of the covariance matrix that make this type of the number of parameters basically to not to grow quadratically with d, but maybe linearly. So let's see what type of restricted forms of the multivariate Gaussian we can have. So here is a case where maybe I make my covariance matrix to be a diagonal with elements sigma 1 square, sigma 2 square, etc. And in this particular case, for this sigma, if you plot the equal contours, equal probability contours that we discussed earlier, basically the ellipse or the ellipsoid in general that you get is aligned with the axis x. And then you can even restrict further, of course, the multivariate Gaussian. You can actually make sigma to be a diagonal matrix with the same value sigma squared everywhere. And in this case, of course, the equal probability contours become circles in 2 dimensions or spheres in d dimensions. So in this case, the first case, you will need a total of 2 d parameters. You will need d variances in each direction plus d values for the mean. And in this case, you need sigma square, so 1 parameter plus d values for the mean. So you need d plus 1 parameters to define completely this diagonal covariance case. All right. Now, I think this is a plot that we have seen before, showing the general case of a two-dimensional Gaussian that you see here, both in 2D and 3D. This is a 2D Gaussian with diagonal covariances. The covariance is a diagonal matrix, so you can see the ellipse is aligned with the axis. And then, of course, you have the spherical case where the contours are circles, and you can see those in 3 dimensions as well. Okay, I think I already have discussed in an earlier lecture all the limitations of the Gaussian distribution. This is not the lecture to remind you the limitations. This is a lecture to actually tell you that the Gaussian distribution is the most essential distribution in all of statistics and machine learning. And at the end of the day, everything is written in some form of a Gaussian or a combination of Gaussians, or some generalized form that maybe integrates Gaussians with some hidden variables. So the Gaussian distribution, it's limited to unimodal distributions, but you can actually generalize it. For example, you can use a mixture of Gaussians, and that will allow you to represent sort of any distribution with as many modes as you are interested. So many of the extensions of the Gaussian to address the limitations, they use latent variables or hidden variables and allow many of the issues to be resolved. So for example, if these hidden variables are discrete latent variables, you can use the idea to write down mixtures of Gaussians. So you can have, imagine you have some weighted sum of Gaussians, okay? So that again can represent any sort of distribution in high dimensions, but also, and this is a more relevant aspect in machine learning, you can actually use continuous latent variables. So you can, you can think of representing in d dimensions distributions that sort of are in the form of some integral of p of x given z times p of z dz, where z is some latent variable and p of x given z is some what we call decoding distribution. And in principle, regardless of what the dimensionality of z is, so you can, the d dimensionality can be 1000 and you can make the z dimensionality being 2, you can actually allow sufficient complexity in the generated p of x to address many of the limitations of the Gaussian. So again, some of these concepts are new here, and we will revisit this when we discuss about latent variable models, but just remember that you can do this generalization with discrete latent variables and continuous latent variables, and this will help us to address all the deficiencies of Gaussians being used alone. Okay, there are infinite generalizations of Gaussians, and I can tell you, for example, when we work with images, it is, especially smooth images, it is always appropriate to actually represent those images with what we call Gaussian random fields, and so we will see this concept hopefully later in the course in some applications. Even sort of in dynamical systems, right? So if you have the evolution of some states in time with some latent variables, so some unobserved latent variables. You can write the combined distribution of observable and non-observed variables as a multivariate Gaussian. So when we do state space models later in the course, we will see how ideas from graphical models can be used to actually produce very complex structures and probability distributions using Gaussian models. Okay, as a matter of fact, I can say that maybe everybody in the audience is familiar with using Kalman filtering, and we will see when we do state space models, for example, that all the algorithms that go under the Kalman filter type of approaches are a small subset of this type of calculations where we use multivariate Gaussians for observed and hidden variables. So again, I don't want you to try to understand everything I said. Just keep in mind here that these limitations of the Gaussian have been addressed in machine learning and statistics with latent variables, and those ideas take us from very complex models for dynamical systems to also very complex models that involve Gaussian mixtures. As a matter of fact, for those who are interested maybe to do a project in this type of ideas, you can even have an infinite mixture of Gaussians. Okay, and of course I haven't said anything about Gaussian processes. Okay, so I'm going to leave this for another lecture. I'm not sure if we will reach the point to cover the topic in this course, but certainly in the advanced machine learning course, this is a topic that is covered over several lectures. Okay, so now what I want to do is I want to introduce for you some linear algebra calculations that are going to be handy, and to demonstrate how handy they are, I am going to do one or two applications on data imputation and tasks like interpolation, so that you can start getting a sense of how powerful this type of formulas are in many practical settings. All right, so let's see what type of algebra we're going to be doing with the multivariate Gaussian. So take a multivariate Gaussian x, right, on the variable x, and split the variable x in two parts, xa and xb. So we're going to partition x in two vectors. Xa, let's say, has m components, and xb has d minus m components. So the vector x is d-dimensional, xa has m components, xb has d minus m components. So obviously, if we partition x like this will imply a related partition on the mean and a related partition on the covariance matrix. So these are the submatrices, right? These are the submatrices defined by the partition of x. And because sigma is a symmetric covariance matrix, sigma AA and sigma BB will be symmetric, and also sigma BA will be the transpose of sigma AB. And I can do the same thing as well for the precision matrix. The precision is also a symmetric matrix, right? The inverse of a symmetric matrix is a symmetric matrix. So I can partition lambda exactly the same way. And again, lambda AA and lambda BB are symmetric, and lambda BA is the transpose of lambda AB. One observation here that I put it in the notes, note that this first component of lambda AA, is not the inverse of sigma AA. All right, that's a typical mistake that a lot of you may do in your calculations. So lambda AA is not the inverse of sigma AA. So when you do partitions of sigma and lambda, do not assume that this is the inverse of sigma AA. The actual relation, actually, I'm going to show it to you a few slides down the road in the lecture today. Okay, so before I start doing any calculations, and the calculations we will do is, to produce the conditional distribution of XA given XB, maybe produce the marginal distribution of XA. So before I do that, I want to introduce this very powerful idea with Gaussians that is called completing the square. It sounds like a joke, right? Completing the square. So let's see what exactly it means, right? So you remember, if I take the exponent in my multivariate Gaussian and expand it in terms that involve sigma and mu, you get this quadratic term plus this linear term. Now let's go backwards, right? And let's say that somehow you do a manipulation of the some exponentials, and when you do this manipulation, you get some term that has x transpose times some matrix times x, all right, and then a linear term. Now you can, when you see something that has these two terms, immediately you can recognize this as the exponent of a Gaussian distribution, where this is the inverse covariance matrix or the precision matrix lambda, and this linear part, the one that multiplies x transpose, is sigma minus 1 times mu. Okay, so again, if we start with the right hand side and after some algebra we get something like that, we know that somehow this we can turn into a Gaussian with covariance sigma and a mean defined through, you notice here, so I have this linear term. So once you identify this and you say this metric sigma is going to be the covariance of the corresponding Gaussian, then you will have this term explicitly in your calculation, sigma inverse m, right? And then you can identify from there what the value of mu is. All right, so if we call, let's say, sigma inverse times mu as a vector m, right? So mu will be sigma times m, where sigma is identified again from the quadratic term. Now, if you want to have a Gaussian that is normalizable, obviously you will have to add and subtract the appropriate constant terms to actually allow you to normalize this Gaussian. And at least when you look at the exponential here, you notice there is an m transpose m term with minus 1/2 on the front. So you're going to need to subtract and add this term to your quadratic form so that you can complete the square. And complete the square means take these two terms that you have here and eventually put them in this quadratic square form, the way we're familiar with for Gaussians. Okay, so all the calculations that I'm going to show you, and some of them they may look very painful and complicated, so you don't really have to follow all the details of what I'm going to do, but you need to be able to use the final formulas, because those formulas, if you have to derive them in every case, it will take you forever to complete your homework or to complete your research. So the final formulas are what we need, and this is what you need to learn on how to use. So let me start with my first calculation, and my first calculation will actually be computing the conditional of p of x a given xb. And an easy way to think about computing the conditional of p of xa given xb is to actually take the joint of xa and xb, all right? So this will be my original multivariate Gaussian. Obviously, it needs to be partitioned because I need p of xa given xb, but take the original p of x, and everywhere you see xb, fix xb to some constant value. Right, so xb, because it's given, is known, is constant. Okay, so when you write the joint distribution of xa and xb, only look at the XA terms, put all of them together, and somehow try to close the square on XA, and that will give you the conditional of P of XA given XB. This is the type of calculation that actually we need to do. I'm only going to highlight. I don't have time to go through all the details. They're given in the slides, and please take the time to at least once see them. So what I'm going to do is I am going to expand the quadratic form using the partition. So sigma minus 1 is the precision matrix lambda. So when you write the partition precision matrix and the partition of x minus mu, okay, in terms of xa minus mu a and xb minus mu b, and you do all the multiplications, this is what you get, right? You get these 4 terms. And now what I need to do is I only need to keep the terms that involve xa. Everything else is just a constant, including xb, okay? I only need to keep the terms in xa so I can identify what type what type of Gaussian, obviously is going to be a Gaussian, is going to come out of this. Okay. So I can tell you there is, I see here XA transpose lambda AA XA. So immediately I see this term coming in here. If you look at all the other terms, there is no quadratic term on XA. So immediately the only quadratic term is this. So the covariance matrix for my conditional of A given B is really the inverse of lambda AA. You remember closing the square? You look at this thing and it better be the sigma of inverse of your distribution, which in our case is the distribution of A given B. So I denote this as sigma of A vertical line B. So this means the distribution of A given B, and that's the covariance matrix of that distribution. Now, if you look at linear terms in XA, I can see here there is XA transpose lambda AA mu A, and then there is another term mu A transpose lambda AA XA, and then I see another term that involves here XA. So if you put all of these terms together, you're going to get what you see here. This will be this will be, if I look on the left hand side, this will be all the terms that involve linear terms in XA. And you remember, if this term is whatever it is, this is what I get when I try to close the square. So what did we say for the mean of this conditional? This whole term here, right, which is written here on the right hand side, it better be sigma inverse times mu, and what is sigma is this precision inverse, all right? So the mean, all right, so the mean comes to be, if you multiply this with sigma, with this particular sigma, all right, so if I multiply with sigma, the sigma is lambda minus 1, so lambda AA minus 1, so this and this will cancel out, and then lambda AA minus 1, lambda AB gives you something like that. So anyways, trivial calculation of closing the square gives you the formula on the bottom, and this is a formula that you will need to use all the time when you try to compute conditionals from a joint Gaussian distribution for XA and XB. You notice, and this has practical implications, the mean of this conditional is linear in XB, all right? So XB, remember, is known, okay? It's linear in XB, but the covariance doesn't depend on XB, okay? And the covariance here is written it comes to be compactly in a very simple way to be given as the inverse of the AA partition component of the precision matrix lambda. Okay. All right. Again, the notation here. Let's be clear, right? This is the inverse of lambda AA, which is the first partition component of the precision matrix on the top left, all right? So that's the inverse of that precision matrix, okay? So this conditional covariance, it turns out, luckily, to be given by this nice expression. Okay, let me introduce this Woodbury formula slowly, and then after we do that, we will come back to complete the calculation for the marginal of XA in a similar fashion to what we have done on this slide, but it's going to be slightly more involved type of calculation. So let me give you the first result that we need to use. If you have a matrix that is partitioned with the matrices A, B, C, D as you see it, and you take the inverse, then the inverse looks at this complicated form where this matrix M that you see on the right hand side is called the surcomplement of our original matrix with respect to the component D. So if you look, the way to remember this surcomplement is, you can see here you have A, and if you go clockwise, minus B, and then you have D inverse times C. All right, so that's the surcomplement with respect to this matrix D. Now, you may ask, where is this formula coming from? For those who want the easy way for deriving this formula, what they can do is they can multiply this formula with the matrix A, B, C, D and convey that they do get the identity matrix. For those who are a little bit more linear algebra oriented, I have a better proof. So if I multiply my A, B, C, D with this matrix on the left hand side, I can get rid of this B and put a 0 there. If I take this result and I multiply with another matrix similar to this on the right, I can get rid of C, and eventually this is the matrix on the right, and I can get zeros in the diagonals. And when I combine step 1 and step 2, I can actually have this times my original matrix times this gives me this wonderful formula. And when I take the inverse when I take the inverse basically of the left hand side, okay, this is this is a diagonal matrix, so I can invert it, and this is my surcomplement with respect to matrix D. So this is M minus 1, this is D minus 1, and when you invert the product of matrices, you're going to have the inverse of this times the inverse of that times the inverse of that. Remember, in inversion, the order of multiplication changes. All right, so the inverse of this will be first the inverse of what you have on the right hand side, and the inverse of that times the inverse of that. And then if you take this inverse, if you multiply basically by the matrices on the left and the right that you see in here, you can actually get this formula, and when you do the multiplications, it will give you what I had listed before for the inversion of A, B, C, D. You can actually write formulas like this where you do use different surcomplements with respect to other matrices, so you can actually write a similar formula where you use the surcomplement with respect to the matrix A, and later on I am going to give you that expression, because when you combine these different sort of expansions that you get this way, you can get different valuable equations by equating these block matrices from these different expansions. And actually we will do this because that's what it leads to the Woodbury formula. But before doing anything anything else on this, let me summarize that this is what we got when we use this inversion of A, B, C, D. Okay, and so now what I'm gonna actually do is let me see what happened, why. Oh, I see. Okay, so you remember I already mentioned, right, that in our inversion of A, B, C, D, we have the surcomplement with respect to the matrix D, and actually what you see on this slide is the similar formula that I mentioned, where the surcomplement is with respect to the matrix A. So you can see here, this matrix M is different from before, is D minus C A inverse B. If I go in a clockwise direction, D minus C A inverse B, and it gives me this expansion. So effectively, I have two inverse decompositions, one where I use the surcomplement with respect to the matrix D, and one with respect to the matrix A. And if you put those together, right, they're all the inverses of this matrix A, B, C, D. Obviously, these block components, these block matrices in blue have to match, and these block matrices in red, they also have to match, because they are again the same blocks of the inverse of A, B, C, D. So if you put the blue on this equal to the blue here, and the red here equal to the red there, you get these two, you get basically that this is equal to this, this is the blue, right? And this is the red equation by equating the two terms, and this is what we get. Again, how do we get this? This is the expansion of the inverse when we use the D complement, the complement, the surcomplement with respect to D. And this is repeating the same thing, but using the surcomplement with respect to the matrix A. And then I'm equating the blue matrices and the red matrices. So this blue matrix is equal to this blue matrix, and this red matrix is equal to this red matrix. So what you actually see, these two equations are going with the name as the Sherman, Morrison, Woodbury formula for partition matrices. You may say, I have no idea why are we doing this and how this is going to be useful to anything I'm supposed to be learning in this class. So I'm going to do one example for you just to get motivated. But let me also give you without proof, but it's actually trivial to prove it based on what you see on the slide. If you take the determinant, all right, if you take the determinant of A minus B D inverse C, this is equal to the determinant of D minus C A inverse B times the determinant of D inverse times the determinant of A. Again, this formula with the determinants, it doesn't look practical, but if you are diligent enough to look at proofs later on that you'll be doing, for example, in the context of Gaussian processes, you will see that this determinant lemma is fundamental in the derivations that we have to do in that area. So let me sort of use one of these Woodbury formulas and tell you what the practical significance is without referring to any specific example, okay? So what I'm going to do is I'm going to take a very limited case of this formula. All right, so I'm going to take a matrix A that is n by n diagonal matrix. So this can be a diagonal, let's say, covariance matrix, okay? But it's n by n, and you can think actually of n, if it helps, think of n as the number of data points, okay? Well, actually, so let me remove for the practical significance because I'm going to have to say lots of other things that will move us away from this lecture. But let's say A is a diagonal matrix, n by n. Okay, so B is equal to C transpose. So Bn equal to C transpose, and they're of size n by d. All right, they're of size n by d. Where the assumption here is that n is much bigger than d. Okay, n is much bigger than d, and d inverse. All right, so we have 4 matrices, and d inverse, I'm going to take it to be minus the identity matrix of size d by d. Okay, again, sigma is n by n, n is way bigger than d, b and c, I take them to be n by d, and d inverse to be minus the identity. So if you plug in all of these things, what you get is that the inverse of sigma plus x transpose, all right, that's the inverse of sigma plus x transpose, is equal to this complicated expansion. But you notice in here I have x transpose sigma inverse x, and if you follow the dimensionality of the matrices, you realize that the matrix that you have to invert is not n by n, but is d by d. And that's exactly when this Woodbury formula turns out to be very essential in our calculations. It may allow us to take the cost of a very expensive n by n inversion and transform it to an inversion of a matrix that is d by d, okay, where d is way less than n. Now, I remind you from linear algebra that if you try to invert an n by n matrix, the cost is of the order of n cubed. The cost here is of the order of d cubed. So if, let's say, n is 1,000,000 and d is 1,000, so you go from 1,000,000 to third power to 1,000 to third power. So obviously the benefits of using the Woodbury formula are significant, and so we will cannot escape. You cannot go and invert this huge matrix when you know you can actually drop it to a much substantially less significant cost and the inversion of a d by d matrix. Let me give you another example. And actually, I said I didn't want to say lots of details here, but this matrix X, for example, that I use here of dimensions n cross d can be what is called your design matrix. And the design matrix is the matrix that contains your data. So think of a matrix that is of size n by d, where every row is one data point, and every column corresponds to a different dimension. All right. So X is your design matrix, and then you can actually put physical meaning to X transpose, right? In terms of the sample covariance, so you can actually start extrapolating where this type of calculations may be useful as we move forward. Okay, and actually in the same spirit, let me use the Woodbury formula to show you that with substitutions for B and C and D that are different from before, and I'll tell you what they are, you can actually show an inversion of the matrix A plus U V transpose using the inverse of A. Notice if this expression that you see here is a direct result of the Woodbury formula, to compute this new inverse of A plus U V transpose, the only thing I need to know is the inverse of A. Okay, this is effectively a rank 1 update of an inverse, and you can think sort of as you collect data points, you want to invert maybe your covariance matrix one data point at a time, and this formula tells you you can use actually your previous inverse and do a few multiplications to actually get the inverse of A plus UV transpose. I mean, otherwise you're going to have to take the matrix UV transpose, add it to A, and do the inversion from scratch, and the cost will be enormous, especially if you have to repeat this type of calculation one data point at a time. Okay, so this again an application of the Woodbury formula, where the only thing we did is we use B equal to U, C equal V transpose, U and V are vectors, column vectors, and D to be a scalar equal to -1, and that leads to this rank 1 update of an inverse of a matrix. Okay, so that's the Woodbury formula. Okay, so we're back to our inversion of this A, B, C, D matrix. So if I apply this matrix to the inversion of the covariance matrix, right, I can substitute what M is. So I'm looking here at the covariance matrix partition like that, like A, B, C, D, and I'm writing explicitly what the inversion will give me. And obviously the inverse of the covariance is the precision matrix. So from this formula, actually, you can immediately see that lambda AA is given by this block here. And so earlier, I believe we had lambda AA inverse. So lambda AA inverse will be sigma AA minus sigma AB, sigma BB inverse, sigma BA. And you can write similar formulas for evaluating these partition components of lambda in terms of the partition components of sigma. Okay, so this can be a very useful quantity. And actually, I can do the inverse as well. I can write this formula for the inversion of the precision matrix, and that's the expansion that you see here. And I can set this equal to the partition covariance matrix. And then you can write that sigma AA, for example, is equal to this inverse, or sigma BA is equal to this matrix, etc. So effectively, when on the in a few slides earlier, I had given you the results for the conditional matrix of XA given XB, I had written those results in terms of the precision matrix, but now you can see that lambda AA inverse is sigma AA minus sigma AB, sigma BB inverse, sigma BA, which is what I have here. And then here you can see I have lambda AA inverse times lambda AB. So lambda AA inverse is this matrix, sigma AA, this parenthesis basically, and lambda AB is this. So actually this matrix and this inverse will cancel, and you get also minus sign. So if you want the conditional of XA given XB, you can express it either in terms of the partition components of the precision matrix, or using these formulas, you can actually use the components, these block component matrices from the partition of the sigma matrix. But again, you notice, don't do the mistake. Sigma AA is not lambda AA inverse. The relation is much more complex, and you see it written in this slide. Okay, so what I need to finish is I need to also derive for you the marginal distribution of XA, and so this will actually be a little bit more involved, because to derive the marginal distribution of XA, what you need to do, you need to start with the joint distribution P of XA comma XB, that's our P of X. And then rather than keeping XB constant the way we did with a conditional distribution, we need to integrate XB out. Let me tell you what the philosophy is so we can avoid the algebra, right? So you have to look at all the terms that involve XB and try to close the square in XB, so that way you can have an integral that is equivalent to marginalizing a Gaussian in XB. And you know how to marginalize XB, right? You know how to marginalize a Gaussian. So if you can close the square in XB, the only thing you'll be left will be a distribution on XA, okay? And because this P of XA XB is normalized, when you integrate XB out and you do it properly, the marginal also will turn out to be normalized as well. So let me highlight without any proofs whatsoever. You expand the joint, and I do it again in terms of the precision. And I mentioned we are going to have to close the square in XB so we can integrate XB out. Immediately here I see a quadratic form. So you know this is my sigma inverse, and this M here that you see is nothing else but sigma inverse times the mean of this Gaussian. So if you do that, all right, and you add and subtract the constant term to close the square. So here I added this, right? This is my new mean. This is my inverse variance, or the precision matrix that comes from this quadratic, okay? So I add this term and I subtract this term, and there's the Gaussian. This first term is a Gaussian. So when I integrate this out, I'm going to get the normalization constant of a Gaussian, and then I have this constant term as well, okay? So what I'm left is actually terms that involve only XA, okay? They involve XA. There is, so if you look at all the remaining terms after XB get out of the picture, you get quadratic terms in XA and a linear term in XA. And obviously what you need to do, this looks to me like the exponential of a Gaussian. You need to complete the square in XA, and when you complete the square in XA, you get a Gaussian in XA, and the algebra is given on this slide in identifying the mean. So immediately you can see that this will be the precision of this marginal, all right? Or this will be the inverse covariance matrix, okay, that you see here. And actually from the previous formulas, if you check the relation between the lambdas and the sigmas, it comes out that the covariance matrix, all right, the covariance matrix for the marginal, that's why there's only one index A, is the inverse of this. And if you go back a few slides, this inverse in terms of all of these lambdas is nothing else but the sigma AA component of the joint distribution of, of the covariance matrix, basically, okay? So in some sense that makes sense, right? If you that's a result that sometimes we use blindly. If you want the marginal distribution, you take the corresponding values of the mean and the variance from the partition of those matrices, and that gives you the form of the marginal of XA. So let me just write the results, okay? The marginal of XA is a Gaussian that has as mean mu A and as variance sigma AA. What is mu A? Is the mean that comes from the partition of the mean of the joint to a vector mu A, mu B, okay? And what is sigma AA? Is the AA component on the left, top left, that comes from the partition, the corresponding partition of the covariance matrix, okay? And of course, we can see that this expression looks very simple in terms of the covariance matrix. If you want to write this in terms of the, if you want to write sigma AA in terms of lambdas, we gave this in the previous slide, but this is actually the easiest expression that you may want to use. So actually these are the two fundamental final results, right, that I want you to remember, so you may want to have them ready to go. The formulas on the bottom give you the Gaussian, that is the conditional of XA given XB, and the formulas on the top give you the marginal of XA. Okay, so now these formulas look like more equations, and somebody says, so why are these formulas of any use? And I'm going to very shortly give you one extremely practical example where these formulas hopefully will make a sense on how they can come together to address some actually serious problems, and most probably our first serious application in this course before we even do any Bayesian modeling. So before I give you that example, there is on the slides, and you can revisit this, there is application of these formulas to a two-dimensional covariance matrix. So I'm not going to go through this. I think we have seen this before, and You can actually, even though the formulas before were for matrices, you can apply them when the partition xa and xb lead to two scalars, x1 and x2, all right? So you can actually define the marginal of x1 having mu1 and sigma1 squared as the mean and the variance, and then you can define the conditional, and I give you plots of this on the bottom of this slide together with the equal probability contours. All right, and this is again a plot that we have seen before, that in principle use these complex formulas but in 2 dimensions. Okay, so and obviously we would like to use these formulas in high dimensions. So let me go directly to this, what I consider not a trivial example but a significant example. So let's do an example. Let's consider the problem of doing interpolation of noise-free data. So we're going to take that we have an integral, we have an interval from 0 to time, let's say t, and we have a signal in time, okay? And so we discretize the time to different intervals distant by some distance h, and let's call the value that we want to, so we're interpolating some function f, right? And yi is the value of this function at the different time intervals ti. And the problem that I want to address is, I want the problem where I give you the values yi at some points on some times, and then you need to compute for me the values of y's at the remaining times on that interval from 0 to times t. All right. So effectively, you can think if you know the values of the function f at some points, sort of for the noise-free case, we need to do an interpolation. We need to interpolate between these points and figure out what the values are at the remaining discretization points. Okay. So the calculation may use a language of Bayesian inference such as prior models and posterior, but really the only thing we will need to do in our calculation will be to use this conditional distribution for Gaussians that we discussed in the earlier slides. And I'm going to try to explain and motivate this. So the problem that we're going to do is noise-free. So the values of the function that I'm going to give you at some points, they're going to be exact. So they're not going to have any noise, which means the fitting that I'm going to do to this function has to pass from these points where I give data exactly. Okay, so we have to, it has to pass exactly. Now, to be able sort of to do any sort of interpolation, we have to restrict ourselves as to what type of functions we anticipate this function f to be like, right? So we need to sort of put some constraints on this function f, and I want you to think of these constraints f as some sort of smoothness conditions, right? We want not to have an extreme variability from one point to another, so we need to introduce some sort of prior assumption over functions, okay? And then, you know, if you think of the Bayes rule, if you have some prior assumption on the functions and the fact that we have data, we have the value of the function at some points, we are really looking over some posterior over functions. I know I'm throwing a lot of you to you there, right? Priors over functions and then posterior over functions, okay? But again, this terminology will not be essential to solving this problem because I am going to drop most of the calculations to that of computing a conditional Gaussian. So we will see this in the slides to come. The original reference from this is the book by Calverti and Eric Somersalo on Introduction to Bayesian Scientific Computing. and I know Kevin Murphy has this example as well in his book, and actually does give a numerical implementation for those who want to look at it. So let's visit the details of the problem. So we are going to discretize the time to locations Sj, where Sj is j times some distance, some time step h, where the time step is t divided by d, and j will be from 0 to d. Okay, j will be from 0 to d, and we're going to call the values of the function. I don't know why before I had a y, but here the y became an x, right? So it doesn't matter. So that's the value of the function at the location Sj. Okay. So what I'm going to do is I'm going to introduce some smoothness constraints for the function f, so we can limit ourselves to functions that they don't vary too much, so we can solve the problem. And the smoothness constraints are of the following form that you see on this equation. Effectively, I am saying that at each location j, the value of the function should be the average of the values of the function to the left and to the right in my discretization on my grid, plus some noise that I take it to be a Gaussian noise. Makes sense, right? You don't want the value of the function to vary too much, so you take it to be the average of the x on the left and the right. And also, you don't want to be very strict, so you allow some noise to come in the picture, right? All models have noise, and we take this noise to be a Gaussian, and the precision of this noise, I'm writing it here for j1 to d minus 1. I'm taking this noise to be this Gaussian with some precision epsilon. Okay, so this sort of is going to constrain my x's not to vary in a violent way, but of course everything depends on how big or how small the precision is. So if lambda is, the precision is very high, all right, the noise will be very small, and we're going to have a very smooth function. On the other hand, if I have a very small precision, the function that I will get, it will actually oscillate between grid points. It will be more wiggly. So again, all depends on what values of lambda I use in the analysis. Now this equation here that I wrote for each grid point from 1 to d minus 1, and you notice, by the way, I don't include the points j equal to 0 and j equal to d, because if you take the point j equal to 0, you don't have a point to the left, right? I mean, I can fix this if I want to, but I don't have a point on the left. So maybe if it helps you in the follow-up analysis, when I give you prescribed data, you may want to consider that the values of the functions at the point j equal to 0 and j equal to d are given, all right? So from all the points that I'm going to give you what the function is, consider that those 2 points are also included, so that way you don't have to worry about j equal to 0 and j equal to d, where this equation is not applicable. So I can write this equation in a matrix form, all right, by introducing this matrix L, all right. You notice that each of these equations, when I multiply with all my vector, when I multiply with all my vectors of the values x, okay, involves a calculation that it has, if I put 2 here, and I remove these x's to the left hand side, then I have a stencil that has 2 times xj minus xj minus 1 plus xj plus 1. So this matrix X is of dimension d minus 1 times d plus 1, because this equation that I have here can be written for d minus 1 points, but the total number of the x values that I have is actually d plus 1, including the points at j equal to 0 and j equal to d. Again, this matrix L is of dimensions d minus 1 times d plus 1, okay? So it's not a squared matrix because I can only write the smoothness assumption for d minus 1 points. Okay, so remember now that the noise that we assume in our smoothing assumption was Gaussian, and so L times x, and x involves the values of the function at all points, is this Gaussian with the precision lambda. So I don't have to really tell you this, right? But if you call L times x y, so y follows this Gaussian, and if you do transformation on variables, then immediately you can see that p of x is actually following this Gaussian, where now you notice that the covariance matrix here scaled by lambda becomes lambda transpose L transpose L. Okay. Now again, how do I get the distribution of x to be this? If you call y equal L times x, right? So p of y is a Gaussian, so in the exponent you have of this Gaussian here, you're going to have minus lambda over 2 y transpose y, and y is L times x, right? So that's from where you're going to get minus lambda over 2 the L2 norm of Lx square. Again, so basically the only thing you have to do is take this Gaussian for y and then plug in y equal L times x. Okay, and I don't bother for the Jacobian of the transformation. That's why I'm writing this thing here like that. So my assumption, my prior distribution over the values of the function is given by this wonderful Gaussian. Okay. Just to simplify the analysis, what I'm going to do is I'm going to incorporate this lambda inside my matrix L, so I don't have to carry this calculation, so I don't have to carry the lambda explicitly out, but maybe, if you want, you can repeat this calculation by leaving lambda as is, because it may come to play an explicit role in the type of results we will get at the end of the day. So I remind you the matrix L is d minus 1 times d plus 1, so it has rank of d minus 1. It's an improper prior, but actually we will see that when we try to compute the posterior, it will lead to proper calculation, so the posterior will be well defined. The only thing that we need to be able to estimate the values of the function at points where we don't have data is we need to have at least 2 data points. Okay, so in the worst case, you can think that you need to have 2 data points at the end of the time interval at j equal to 0 and j equal to d. So so I'm going to incorporate lambda inside the precision matrix, right? So I'm going to scale the precision matrix to incorporate lambda inside, and so when you expand this, right, you're going to get a precision matrix that is L transpose L, right? That's what we have here. So what I'm going to do is I am going to partition the matrix L to a fashion that accounts for the grid points where I provide data and the grid points I don't have any data. All right. So let me assume that I am partitioning the way we did in with a multivariate Gaussian. I partition my vector x, that's the values of the function, in a vector component x1 that has d minus 1 unknown components. D are all of my components, n is the components where I know the values of x, and those values are x2, these are where I provide the locations where I provide noise-free values for my function. So I partition again x to d minus n unknowns and n known values. So you can think again, this partition doesn't need to involve components in the grid that they are sequential, but in principle what I imply here is take all your x's that there are knowns and put them on the top of the vector, and take all the x's that they are known and put them on the bottom. So if you do that, this implies a similar partition of the matrix L to a matrix L1 that is of dimensions d minus 1 times d minus n plus 1, and then a matrix L2 that is of dimensions d minus 1 times n. So when you form this precision matrix L transpose L and you write it in a partition form, you get a matrix that has these components, okay? And again, what is L1, L2? This comes from the partition of the vector x to unknown components on the top and the known noise-free components on the bottom. Okay, can you actually see now how I am going to compute the unknown quantities? I have a Gaussian, all right? I have a Gaussian, P of x. I have partition x to x1 and x2, and I know x2. So what I need to find is, I need to find the probability of x1 given x2. Do we know how to do this? Yes, of course. We derived before the conditional distribution of x1 given x2. So I'm going to cut and paste the previous formulas, which for your convenience are given here. And I'm going to substitute lambda 1,1 and lambda 1,2 from the previous derivations in terms of L1 and L2. And here is the answer, all right? So immediately we can write down a conditional of x1 given x2. It's a Gaussian, and effectively this Gaussian will allow us not only to figure out at the grid points where we don't know the function, what the function values are in the, as mean values, but also we're going to be able to say something about the error bars, right, the confidence on these predictions x1. Literally, it's like doing full Bayesian setting, even though I only introduced a prior model and then I took that prior and I specify some data. So effectively, you can interpret this model as the posterior of x1 given by data x2, but literally for this lecture, I am not doing anything more but sort of using this conditional for Gaussians, all right, and producing using the formulas of x1 given x1 given x2. Okay, if you L1 transpose, by the way, L1 is a square matrix, is invertible, so there is everything is wonderful, nothing is wrong. Now, if it happens that you have only two data points, so for example at S0 equal to 0 and SD equal to t in on the left and the right of your time interval, then it turns out that L1 is invertible, and this equation that I have here for the conditional mean can actually, this calculation of the conditional mean can be simplified as the solution of a linear system of equations that looks like that, because effectively here you have L1 inverse and L1 minus transpose with L1 transpose cancel out, and if you put L1 inverse on the other side, this equation here becomes equivalent to solving a linear system of equations for this conditional mean, in principle this posterior mean, if I can start using that expression. So let me give you a few results. And this is, there are two pictures here. I put back the precision lambda, and in one case the precision lambda that I use is very high, so the uncertainties in the predictions will be smaller. In the case on the right, the precision is very small, so the uncertainties will be very high. What are these crosses? These are the noise-free data that I provide. I cannot actually see, well, I want to assume that this curve here that you see, the black curve, is actually the conditional mean or the posterior mean that the model predicts. And then these painted areas correspond to plus minus one standard deviation from my conditional mean variance or my posterior uncertainty, if you like. You remember the conditional distribution was a Gaussian. I know the variance of each component. I actually, if you want, you can marginalize them, right? And here what I'm plotting is I'm plotting plus minus one standard deviation. Now the picture on the right shows much higher uncertainty because the precision is much lower, but again I am forcing the function to pass through these data points. What are the other curves? They're also very significant. You notice these other curves are wiggly. So the other curves, what they are samples of x1 from this conditional Gaussian. So rather than taking the mean and plotting the mean, what actually you're doing is at all the locations where you don't know the function, you sample it, and each of these are samples from this multivariate Gaussian that corresponds to p of x1 given x2. Actually, later on when we do Gaussian processes, these pictures that you see here will be an identical picture that you will get with Gaussian processes. And somehow we have been able to actually derive all of this simply by using the result of conditionals derived from a multivariate Gaussian. Of course, we will see that Gaussian processes are nothing else but sort of infinite multivariate Gaussians, but we will see they're defined on a continuous grid rather than the discretized grid that you see here. Obviously, here I have connected the points in my grid. That's why you see a continuous line. All right. So x1 is the function at a discrete set of points. Is not on a continuous set of points. With Gaussian processes, we will get similar graphical representation, but the calculations would be over a continuous set of points. So this is the plus minus one standard deviation that I mentioned before for this credibility posterior intervals, if you like. So this will give you the error bars in your predictions. That's a wonderful thing. And let me mention only one thing, and this comes, the derivation, I am not providing it here, but it comes from the textbook of Calvetti and Sommersalo. So the idea here is that if you force the data to pass from some points noise-free, so we're forcing the curves to pass from these points, what happens is the uncertainty is becoming bigger because whatever is happening away from these points, we have to come back and pass through these points. Now, if somehow we allow some error bars in the provided data, so if my data, they're not actually precisely given, but they follow a Gaussian with some covariance that here I take it as a diagonal matrix, you can actually repeat the same calculations that we did before and show that the probability of of your function values at the unknown locations turns out to be a Gaussian. All right, turns out to be a Gaussian, where this matrix gamma that we had before has to be adjusted now to incorporate the covariance in the given data x2. Again, in this case, the data x2 are noisy data. So this covariance matrix C is represented here with these error bars that you see in the given data. So the given data at these points can be anywhere within the, let's say, these intervals, okay? And so we don't really force the posterior solution to pass exactly through these points, and that results in reduction in uncertainties, as you can see on the picture on the right versus the picture on the left. Okay. Actually, this to me sounds like a very good homework problem. So most probably I will be asking you to actually program this noisy data case in your next homework assignment. Okay. Let me just in brief mention the data imputation problem, and for more details you can consult Kevin Murphy's toolbox. Suppose I give you a Gaussian, right, of dimensionality D, all right, and I'm looking at the design matrix. The design matrix is the matrix that contains the data points. So every row is one data point of dimension D, all right? So if you look at it, each point, each row is a sample from from a multivariate Gaussian. So what we're going to assume is that this big matrix that involves this design matrix of data points has a lot of components missing, all right? So if you look, let's say, in a particular row, a lot of the components corresponding to multiple dimensions are missing, and the data imputation problem is knowing that these rows come from a multivariate Gaussian in D dimensions, to go and do predictions on the missing elements in your design matrix. Again, what do you need to do is you need to basically produce exactly as we did in the earlier example with interpolation. You need to produce P of x1 given x2, okay? x2 are the given elements in each row and x1 are the missing elements, and this corresponds to the so-called data imputation problem. So the fact that you know that these data are not, they come with some structure, the fact that you know that these data are being generated from a Gaussian model, you can use that to compute what is missing given what is known, and this is effectively compute in each row, let's say I, the hidden elements that you don't know, given the visible elements of x in each row I that you know, and here theta are the underlying parameters of the Gaussian, and I believe in the results that are duplicated on the slides, the parameters that are being used are the true parameters of the Gaussian, but basically you can also go around if you want to and try to either evaluate those using the visible parameters, the visible values x, or somehow iteratively update theta and these hidden values in a way that will make this to converge. But in the results, the parameters theta use, so the mean and the covariance are the true values, right? And you only do this conditional distribution as we highlighted in the previous example, and also in the general formulas that we produce. Okay, so you can go to the rows where there are missing elements, and actually you can do imputation, and you can compare with the true values, and the results look quite well. And also, not only you can compute the mean of this distribution, but also you can compute confidence intervals, because this distribution is a Gaussian, so you know the marginal of this Gaussian. So for each location ij, effectively you know what the marginal distribution is, so plus minus one standard deviation of that Gaussian will give you the error bars. Okay, you can even actually do outlier detection if you like, and in some sense you can do that calculation by using the visible data, the data that are provided, and trying to compute the likelihood of that data with respect to the true model that you are given. Okay, so you can do lots of fancy things like that. Okay, this has been a long lecture, so let me finish by giving you 1 or 2 slides of what's called the information form of a Gaussian, and then we are done. So if you remember, up to now, all our calculations are using a representation of the Gaussian in terms of its moments mu and sigma. So there is another form that is used especially in the context of the exponential family distributions, that uses what is called natural parameters. So the representation is called the natural or canonical representation, and we usually use n subscript c to indicate that the parameters are these natural parameters. And the new parameters that are being used is first the precision metric, so that's not new, right? But instead of the covariance, we use the precision metrics, and instead of mu, we use a vector xc, which is basically the precision metrics times mu. Now, I'm not going to do all the algebra, it's on the slides. Okay, so let me say if you take your classical exponential in your Gaussian in terms of mu and sigma, and you change the variables mu and sigma to lambda and xc, this is what you get. All right, and the equation that you see on the bottom is the canonical representation of a multivariate Gaussian in terms of the parameters xc and lambda. So when you see nc, the variables are xc and lambda, and again, you have a quadratic and a linear term in x, but instead of mu and sigma, you have parameters lambda and xc. Now, almost all of the results that I mentioned before, you can actually repeat them, and I wouldn't advise that you do that because the calculations may be very long, but in principle you can repeat those and write down the marginals of a Gaussian, the condition, and all of these things in terms of these natural parameters. So I'm going to actually give you one result on the bottom of the slide for the conditional of xa given xb. So it turns out that the natural parameters for this is a covariance matrix lambda AA, and the xc parameter for this conditional is xa minus lambda AB xb, and xa comes from the partition of the vector xc corresponding to the partition of x to xa and xb. Okay, so again, xa is coming from the partition of that vector xc when you partition x to xa and xb. So actually the definition of xa is formally given here. All right. So if you remember, the lambda times mu is equal, lambda times mu is equal to xc. So here what I have is actually when you partition lambda and you do the calculation of xa, you will be multiplying lambda AA mu A plus lambda AB mu B, so that would give you xa, and similarly xb would be lambda BA mu A and lambda BB mu B. So anyways, the conditional of the of the Gaussian for in this natural canonical form looks very simple. And let me give you another result to actually motivate you why this canonical form may be very handy in certain cases. So I am not going to go through this derivation here. So this is basically discusses the canonical form for the marginal. All right, so this gives you the canonical form for the marginal if you are interested, and actually the formula for the canonical form of the marginal looks more complicated now actually than in the moment form, is given from the equation that you see in the bottom involves these partitions of the xi vector that I discussed before and the partition of the precision matrix. But let me give you one example that I mentioned. If you take the product of two Gaussians in a moment form, so let me actually start with the equation on the bottom. If you multiply two Gaussians with means mu1 and mu2 and sigma 1 squared and sigma 2 squared respectively, you get a Gaussian that has this mean and this variance. Now, if you do this multiplication in canonical form, you get a wonderful result that the new precision of the product is the sum of the two precisions, and the xi parameters for this product is the sum of the x's for the two Gaussians. So this is a much simplified formulation. So when you have products of Gaussians, remember this formula. It may turn out that it's much simpler to do the calculation in canonical parameters rather than using this moment parametrization. All right, so there's been a lot of formulas, and again, if there's something that needs to stay from this lecture is this idea of closing the square of a Gaussian on the formulas that we produce for the conditional and the marginal when we partition the vector x and we partition the covariance and precision matrices. Using these formulas for practical tasks like interpolation in the noise-free and noisy data situations. And then just remember that there is a parametrization in terms of natural parameters that may be handy, in particularly when you compute products of Gaussians. That's all for the lecture. I'll see you next Thursday. Bye.